Hi everyone, welcome to the monthly IOP lectures held at the Open University. Sorry for the late start, we've been experiencing a few technical difficulties, but I'm going to host the slides for Jess, and she's going to let me know when to change the slides as we go through. So welcome everyone, finally. This is our third online lecture in this series, and we hope to resume in-person meetings as soon as it is safe and responsible to do so, but that means it's probably likely that we continue in this format for some time to come. You can find our previous stream talks on the OU School of Physical Sciences YouTube channel, and this lecture will be recorded and uploaded to the YouTube channel at a later date, and you can re-watch it through this same stream link that you're viewing now, probably within the next day or two. As you can see, we're live streaming a call today. That's for everyone's internet safety. But you can interact with the speaker by sending your questions in through email to stem.sbs-iop-lecture@open.ac.uk, and that link should be on the Stadium page that you're viewing from now. And we'll ask as many questions as we have time for at the end of the talk. Also, you'll see on Stadium there's a link to a short demographic survey. We'd be very grateful if you could take the time either now or during the talk to fill in this. It'll only take a couple of minutes. The data is entirely anonymous, and it gives us insight of how effective our marketing is being at reaching a large audience for these lectures, and if there are any communities that we want to focus and market to. I would like to bring your attention to another talk. This is not an IOP talk, but this particular IOP talk is part of the OU's celebration of the 48th anniversary of the Apollo moon landing. So that's an event that we call Moon Night. There was a families event yesterday online. Tonight we have this lecture, and then tomorrow night you can see on the screen there's details of a Colin Pillinger memorial lecture, which is part of this series of events as well, which is about Mars and planetary protection by Dr. Andy Spry. If you just type in, I've shortened the URL there, so if you go to http://tinyurl.com/Pillinger, that should, I'm not sure if the capitalization matters, that should take you to an Eventbrite page where you can register for free to attend that talk tomorrow evening. In terms of this series of talks and upcoming talks in this series, traditionally we don't hold a lecture in January due to risk of it being rained off. However, now that we're online, we're looking to fill a slot on the 12th of January. We're still ongoing penciling a speaker for that date, so please keep an eye on your email inboxes for marketing emails about that, and I'll give you some details of how to join that in the future. However, we do have a very special lecture on the night of February the 9th. Professor Nick Braithwaite, who was recently awarded the Institute of Physics Bragg Medal in recognition of his work on the Open STEM Labs, which is an initiative which has given OU students access to lab equipment for experiments, regardless of where they are in the world. Nick has been awarded that medal, and he will be giving a talk on February the 9th around the Open STEM initiative in commemoration of his receiving of that award. So that'll be a bit of a special IOP lecture that evening. We will advertise through our normal routes. So that's through the IOP mailing lists, which you can send an email to emailmarketing@iop.org and ask to be added to the Milton Keynes Talks email list, and you'll be subscribed to that mailing list. You can follow us on social media. We advertise all these talks on social media a couple of times in the run-up. And there's also, I believe, on the page you're looking at now, a link to SBS outreach mailbox, which you can send an email to and ask to be subscribed to our outreach mailing list as well. There's a few ways that we can get in touch with you and let you know about future talks as they come up. So I think that covers everything that I wanted to say. There's going to be maybe 30 seconds while I'm trying to switch over my slides to Jess's slides, but it gives me great pleasure to introduce Dr. Jessica Barnes. I've known her for a number of years. She did her PhD here at the Open University under Professor Mahesh Anand, investigating water in moon rocks using novel techniques. She received her PhD in planetary and space sciences in 2015, and after a short postdoc at the OU, she moved to Houston, Texas, where she was a NASA postdoctoral fellow at Johnson Space Center. She then started her position at LPL, University of Arizona, in autumn last year. Her research centers now on understanding the origin and evolution of volatiles in the inner solar system. So I'll give it over to Jess as soon as I sort out the slides, who will be giving her talk entitled The Moon's Water, Past, Current and Future Perspectives.
So thank you very much, everybody, for joining me this evening or today, whatever time it is, wherever you are. I'm really honored to give this IOP talk. I remember going to IOP talks when I was a PhD student and postdoc at the OU, and it's just a shame I can't be there in person. But thank you for everyone for joining me tonight. I'm going to kind of give an overview talk about what we know currently about water on and in the moon and how that knowledge is driving future lunar exploration and also current lunar exploration. So next slide. Okay, so the structure of my talk is going to be starting off with an Apollo era perspective and then moving into kind of research from the last 15 years of studying moon rocks and also studying the moon from orbital missions and remotely. And then we'll move on to discuss some of the exciting new work that's going on, looking at new lunar samples and then also future perspectives with regard to exploration. Next slide, please. And so we'll start off with the Apollo era. Next slide. Okay, so following the Apollo missions, the first landed but also orbital missions, you see here an oblique image from Apollo 8, a photograph taken from orbit. The Apollo astronauts really did not see anything either remotely or while they were performing surface operations that indicated that liquid water was present at the surface. Unlike what we see on Mars and what we see on Earth, there's no evidence for seas or lakes or rivers on the surface of the moon. And so it suggested that there wasn't any surface water. When moon rocks were brought back, they were of course studied for assessing if there was any water in the rocks, because actually looking for water and looking for the signatures of life outside of Earth were some of the key science drivers for the early Apollo missions. But when Apollo scientists started analyzing the rocks, they quickly realized that there were no hydrous or hydrated minerals in lunar samples, at least that they could detect with the technology at the time. On Earth, we have lots of minerals like amphiboles and micas that contain water in their crystal structures in several weight percent levels, and we just didn't see those in the lunar samples. And then finally, in rocks, we see the presence of native iron, so iron present as a metal and not as an oxide. And so that indicates a relatively low oxygen fugacity or availability of oxygen in the lunar environment, which was another indication that...
Hi, Jess.
I do not happened. I apologize for that, technical difficulties. So we just talked really briefly about what the Apollo astronauts saw and what the Apollo era scientists saw in the lunar samples. But when they actually started to measure water in the samples, they did that via stepped heating. So looking at bulk materials, either soils or volcanic rocks. And as I said, they did that by step heating. So gradually heating up a sample and seeing what water molecules or water species came off. And they didn't just measure the abundances, they also measured the isotopic composition of the water and hydrogen that was being released. And on this slide, you can see up at the top, there's an equation. And when we're describing the isotopic composition of water in these types of samples, what we're really talking about is a deviation in the deuterium to hydrogen ratio. So those are deuterium and hydrogen are two different isotopes of hydrogen, with deuterium have an extra neutron compared to hydrogen. And so, oh, saying I've got bad quality again. Are you still there, Ben?
Yeah, you're breaking up a little bit, but it's still okay.
Okay. We will. And so we describe this hydrogen isotope composition as a deviation in the deuterium to hydrogen ratio of a sample compared to standard in value in per mil or per thousand. And so
Jess,
what this
sorry.
Yeah.
Do you want to try turning off your camera?
And so what we see then is, sorry, my dog's looking her cage. So what we are looking at is a deviation in this isotopic ratio compared to our standard, which has a nominal deuterium or delta D value of 0 per mil. And so what the Apollo era scientists started seeing when they were looking at these lunar soils and rocks that were being brought back was that they were seeing a variation in this isotopic composition that you can see in the bottom panels, and also in the hydrogen, molecular hydrogen, and the water extracted from these samples. And so, but what they weren't able to do, even though they were detecting water and hydrogen, the isotopic compositions were not, they didn't think they were lunar. So they thought they were seeing a mixture of terrestrial contamination. So if you look at the bottom right panel of this diagram, at the upper, the squares, they thought they were seeing water from the terrestrial atmosphere mixing with a really low, kind of trending towards minus 900 per mil deuterium to hydrogen ratio of solar wind. And so really in the Apollo era, there was a lack of unambiguous detection of lunar water in these materials. And they thought it was this mixture of extra lunar water and then even terrestrial contamination. And interesting, after the Apollo 14 samples were analyzed, NASA decided to relieve their biological protection and quarantine of lunar samples because they just hadn't detected lunar water or organics in levels that they thought were a danger to the people analyzing them. Next slide, please. And so these observations really led to the idea, looking at the lunar samples, using the observations from the ground and from remote sensing or remote observations by the astronauts, that the moon was a dry place, bone dry, with very little water to speak of in its interior or at its surface. And so, go to the next slide, please. And so this paradigm is important to realize because the Apollo era really set in motion the constraints with which we would then place on our models for moon formation and how the moon evolved over time. And so the left set of figures here show you the canonical model for how the moon formed. So we think the moon formed in a giant impact event and with an object potentially the size of Mars, hitting the proto-Earth. And then a mixture of material from the impactor, but most of it from the Earth's mantle, was flung out into space and accreted in Earth orbit to form our moon. But that model for basically the last 50 years did not include water in that model. Equally, models for how the moon then solidified after that and how it magmatically evolved and thermally evolved also neglected to include water in those models, the so-called lunar magma ocean model that you see depicted on the bottom right, where you start off with a potentially globally molten moon or partially molten moon, and then you start crystallizing out mafic minerals, and then eventually you form a flotation crust on the moon made of anorthosite and anorthite crystals. And then after some time, you start crystallizing out really dense materials, being ilmenite rich in iron and titanium. And then that subsequently reorganized itself to form a very heterogeneous mantle and then gave rise to the volcanic activity we now see pockmarked all over the lunar surface as the dark regions, the Mare regions. So the point here is that the Apollo era examination of moon rocks and also the lunar surface kind of set in motion this idea that the moon was bone dry and that all of our models and understanding of the moon were cemented in that idea. Next slide, please. However, moving forward, in the last sort of 15, I guess more than that now, maybe 22 years, there's been this revolution or renaissance in our understanding of water on the moon and in the moon. And so we're going to first of all take a look at surface water. And so, Ben, if you can go to the next, please. Thank you. And so really the discovery of lunar water on the surface really started in the mid-1990s. And the NASA Clementine mission in 1994, but the results were published in 1996, used a biostatic radar experiment, which the results of that indicated there might be water ice present on the surface. But they didn't have the spatial resolution really to quantify how much might be there, or whether it was in craters or on the surface outside of craters. And so it wasn't until Lunar Prospector, another NASA mission which had a neutron spectrometer, that was actually able to indicate hydrogen to a depth of about 1 meter. And so the reason why the neutron spectrometer on Lunar Prospector is important is because the neutron spectrometer and spectrometry as a science is really sensitive to the presence of hydrogen at the surface. And so that's because neutrons, which are produced by cosmic ray interactions with the surface, essentially are slowed by the presence of hydrogen. And so you can then map out where you see these neutrons either moving fast, with medium velocities, or slow, and then you can pinpoint where hydrogen is on the surface. And so you see that in these polar region maps from Lunar Prospector. The darker blue regions and purples and pinks, those indicate high abundances of hydrogen at the lunar north and south pole, respectively, above and below. And so this was a really early indication that there might be water ice scattered inside craters at the lunar poles. Next slide, please. Okay, and so if we progress a little bit further in time, we get to sort of the mid to late 2000s. And you know, Lunar Prospector and Clementine have shown tantalizing evidence that there might be lunar water at the surface, which again is a revolutionary idea compared to the Apollo era. And so next we herald in the NASA's Moon Mineralogy Mapper, or MCube, which was a spectrometer on board, or an instrument package on board the Indian Space Research Organization's, or ISRO's, Chandrayaan-1 mission. And this is a spectrometer that is able to identify the diagnostic absorptions of hydroxyl, so OH, and water. And so it's sensitive in the range of around 3 microns. And what MCubed saw, if you look at the color composite at the top right-hand side of your screen, you see a 3-color composite of the reflected near-infrared radiation that's coming from the sun. And then this map is basically showing you the distribution of water, but also of minerals at the lunar surface. So the blues and purples, again, are highlighting where hydroxyl or water was detected at the surface. The green is showing surface brightness, and then the reds are showing the presence of iron-bearing minerals at the lunar surface. The key point from this, if you look in detail, water, or hydroxyl and/or water, was detected all over the lunar surface in varying abundances, more concentrated towards the poles, but all over the lunar surface. And so if we fast forward to 2017, this figure by Lee and Milliken, their study, they looked again at MCube data, but this kinds of spectroscopy involves using a thermal model. And so they changed the thermal model to come up with a more updated abundance distribution of water at the lunar surface. And so here again, you see, although this is stretched out, you can see that at the polar regions, we see higher abundances of volatiles than we do, or water than we do at the equatorial regions. And so here we're seeing hundreds of parts per million of water. So a very different story to the Apollo era. I will just note that up to kind of this point, most of the spectroscopy that's done around the moon is looking at hydroxyl, not looking at molecular water or hydrogen. This is because
the limits of the spectroscopy that can be done in this kind of near infrared range are most sensitive to hydroxyl, which is, if you look at the little spectroscopy reflectance wavelength diagram, the OH band is the black, and that's far from this 3 micron limit. Whereas the further you go towards this 3 micron limit, you see here absorptions for water and ice, but we're kind of hitting the detection as we go towards that direction of the instrument itself. And so that's why most of the spectroscopy is detected mostly OH. But the take-home message is water all over the surface of the moon, water being a hydrogen-bearing species, and there are strong absorptions at the poles. Slide, please. Okay, perfect. Okay, so what does this mean in a more global sense? What's happening at the lunar surface, and why are we seeing these deposits from orbit when we weren't seeing them through astronaut observations or seeing them in photographs beforehand? So what we think is happening there, you see on the left-hand side of your screen, this cartoon of kind of what's going on. What's established is in blue, and hypothetical kind of things still to be determined are in purple. And then we have some processes that are in kind of orange or yellow and green. And what we think is happening and actually causing us to see water, ice and hydrogen at the surface is we have solar wind protons, so hydrogen, hitting the surface and being implanted into the regolith. So that's the uppermost kind of fragmented surface of the moon that's ubiquitous across the surface. We see that because we're implanting hydrogen, we can have reduction of iron oxide that's in the surface mineralogy and the surface materials through micrometeorite impacts or larger impacts, which will dissociate and cause there to be oxygen with hydrogen, which will combine with water and form this kind of desiccated monolayer on the surface of the moon. Now, if we follow the orange or yellow arrows, this water on the very most upper surface can be excavated by meteorite impacts. And some of it can escape. So some of it resides in the tenuous lunar exosphere. Some of it can escape through thermal escape or photodissociation, but some of it can also be redeposited back on the surface. It can also diffuse into the regolith below, and create these diffuse hydrous layers that you see on the left-hand side of the screen, right-hand side of the screen, these patchy horizons in the subsurface. And then there might even be larger water ice deposits even deeper in the subsurface as well. And so what this is showing is there's this relationship between sources being solar wind protons. We can have meteorites hitting the surface or cometary impacts that deliver water to the surface. Interaction of galactic cosmic rays can also have an effect. Then we have redistribution across the surface, and we'll discuss this a little bit more on the next slide, either through photodissociation or burial or excavation or thermal loss. And then we have sinks, and we'll discuss that more in a second as well, being areas either in the regolith, in the subsurface, or in areas that are particularly cold, which can actually harbor and trap these volatiles. Next slide, please. Okay, perfect. And so when we think about areas on the moon which would be particularly important for lunar water, we're thinking about the polar regions. And we've already identified that from remote observations that they seem to be the areas that are richest in water. So at high latitudes, topography really creates these cold traps, these areas of permanent shadow. They're really cold, less than 200 Kelvin. So what's that, less than about minus 70 something degrees, so very cold. And they make these conditions which enable water ice to be stable at the surface. And so we can sequester volatiles in those areas. And so in the schematic on this slide, you see the difference between the illuminated moon and the shadowed moon. And so in the illuminated areas of the moon, we have large temperature fluctuations. So during noontime in a particular surface on the moon, you would have the highest temperatures, and that means you can potentially lose some either molecular water that's clinging to grain surfaces, or you can, it's a space and then it can recondense when it gets colder, or you can have this ballistic random walk of water molecules over the surface as you impact that surface continually with, for example, micrometeorites or meteorites in general. And so what's going to happen is as that water molecule or water molecules start moving across the surface, they're going to be sequestered in areas which are more stable for them. And so areas like these permanent shadowed regions in the poles. And so this is this idea of cold trapping. Now, arguably one of the most robust measurements of lunar water at the surface has been through the LCROSS mission. And so the LCROSS impactor was part of Lunar Reconnaissance Orbiter's mission, where the center upper stage of LRO was deliberately slammed into the floor of Cabeus crater near to the south pole of the moon. And then not only did LRO, but also the satellite that was also part of this experiment, they both detected the plume of material, the puff of material that you can see on this figure. So the little circle is indicating the puff of volatiles that are being released from that impact event. And so Orbiter was able to fly through that and detect the species that were present. And then also LRO was able to make some spectroscopic observations as well. And so through this LCROSS impact event, both water vapor, but also water ice was detected in the plume, along with other components such as ammonia, carbon monoxide, methane, and some organic bearing molecules. And so this is really, LCROSS is probably the most well understood and robust measurements that we have of lunar polar water. Next slide, please. Okay, thank you. And so we've seen kind of an introduction that there exists a wealth of information or evidence that there's probably water at the lunar poles, probably sequestered as water ice. There's evidence for hydroxyl. More recently, there might be molecular water all across the surface of the moon as well. And we've seen indications of hydrogen as well present. But one of the big problems and challenges to understanding what's going on the surface of the moon is that there's disagreement between different instruments, and I've only shown you a couple of examples of different instruments that have taken measurements. The difficulties are that they have different spatial resolutions, so they tell you information about water as a broad term at the surface of the moon over different areas. They have been sensitive to different molecules, and they also tell you they're also sensitive to different depths. So neutron spectroscopy can tell you about water ice deposited at kind of the meter scale, whereas spectroscopy near IR, that kind of thing, like M-cubed, is telling you more about the upper couple of millimeters of the surface. And so this has led to kind of this dispute in the community as to what is the lateral and vertical distribution of volatiles, including water, at the lunar surface, particularly in the poles. Are the deposits that we're getting indications of, are they continuous or discontinuous? Are they patchy? Is there a lot of water in the subsurface as water ice? What's the abundance? There are huge discrepancies as to the abundances. So we just saw part per million levels from the Liam Millikan paper, but LCROSS detected up to 5.6 weight% water ice in Cabeus crater. And so taken at face value, there is a lot of merit into better understanding the quantity and variability and abundances and character of volatiles at the lunar poles and across the lunar surface, if we're to start thinking about sending future missions to use those resources in situ resource utilization. The other thing I wanted to point out too is that I mentioned a second ago that permanently shadowed regions in polar craters are very cold, but they're not always cold, and not everything at the poles is permanently shadowed. And so this figure is showing you temperature in the South Pole It's showing you the minimum temperatures are the top two spheres. The middle are the average temperatures across the year, and then the maximum temperatures are on the bottom. And so what you want to look at in the polar regions, is particularly the South Pole, is the top panel, and in particular summers, right? Because the temperatures are going to be hotter in the summer. So you want to look for regions that are blue, which are the colder temperatures in the summer, because those are most likely to be your permanently shadowed regions. But once you look in more detail, once you go to higher resolution on those areas, you see that there are actually lots of variations occurring within craters and between craters. And so it's a very complex situation, very complex environment to deal with. And if we were going to go back to the moon, we need to better understand what these deposits are, where they are, and try to address some of the questions on this slide. Next, please. Okay, so let's move on to talking about lunar interior water. And this is an important distinction to make, because we've talked about surface water. Interior water is really looking at lunar samples, looking at water locked up into minerals and glasses, and using that to try and understand what's going on inside the moon. A lot of the rocks we have are magmatic rocks, so they're formed by melting of the lunar interior. And so by looking at those rocks and the water that they hold and their isotopic compositions, we can start to say something about the magmatic and thermal history of the moon, and potentially where the moon got its interior water, magmatic water. Next slide. And you can just flick through all of these. There's lots of animations. Okay, perfect, thank you. And so following up on the detection of water at the lunar surface, circa 2008, 2009, plus using new state-of-the-art laboratory equipment and using revisiting Apollo samples, colleagues at Brown University, Alberto Sal and Eric Hyrey, discovered lunar water in volcanic glass beads. And so in this figure, you're seeing an Apollo 17 image of one of the stations at Apollo 17, where there's this deposit on the surface of the moon. You can see it's kind of coming up here like a brownish color. And then if you look at the next figure, so going towards the right, you can see these lunar volcanic glasses are orange. And so the Apollo astronauts knew this was something different when they collected this material, and turns out these are volcanic glasses formed by fissure eruptions onto the surface of the moon. Using new laboratory equipment, this group was able to detect at the micrometer scale water inside these glass beads, which they inferred to be lunar water. And they did a lot of, not only has the technology improved, but our understanding of terrestrial contamination and how to avoid it and account for it meant that they were able to unambiguously say that what they were measuring in these samples was lunar and not terrestrial. And so this just was not possible in the Apollo era. And this was a massive step forward in our understanding of how do we look at lunar samples using new technologies to address old questions and pose new ones. Next slide, please. Okay, so from about 2008, we started to work on other lunar materials. And there are several different targets that maybe were not obvious in the Apollo era as being targets with which to study water. But given the kind of last 20, 30 years of instrument development, particularly in secondary ion mass spectrometry, we really pushed the boundaries of what's possible. And so now you can detect very tiny concentrations of water in almost any kind of lunar material, even minerals that aren't supposed to contain water. And so the most popular targets nowadays for studying lunar water include the volcanic glass beads I just showed you, melt inclusions. These are, you can see the figure that has an A on it here, the Hyrey et al. 2011 paper. Melt inclusions are basically trapped parcels of melt. So you can imagine a magma is rising to the surface, or it's trapped in the crust. It's going to start cooling. Crystals are going to start to grow. The earliest crystals that form, minerals like olivine, can trap that melt. And then that melt becomes protected from any processes that occur in the magma after that trapping has occurred. And so when you see melt inclusions, there are some caveats, but generally the inclusions can tell you about the magmatic composition, the very earliest magma composition in samples, in this case lunar samples. The other way we can get at understanding lunar volatiles and water is to look at a mineral called apatite. And you can see the chemical formula here. It's a calcium phosphate mineral. Importantly, it incorporates hydroxyl, so OH, into its crystal structure. Apatite was recognized in the Apollo era, but they didn't have the technologies available to actually quantify the relatively small amounts of hydrogen that are present. And then there's nominally anhydrous minerals, which I won't really go into. Each of these different mineral classes or phases, when you measure water and its isotopic composition, tell you complementary information about the volatile inventory of the moon and of the rock types that they come from. And so studies in the last 10 or so years have been looking at water, and most people report water, but in reality, we're measuring slightly different things depending on the techniques you're using and the minerals you're looking at, and or the deuterium to hydrogen ratios. Next slide, please. Okay, and so you're probably asking yourself, well, how much water has actually been detected in lunar samples? And the answer is it varies. Just like we saw with the surface of the moon, when we're talking about interior lunar water, we also see variations. So between samples, we see variations on the order of several parts per million up to several tens of thousands of parts per million. And so what these figures are showing you, if you look on the left-hand side of your screen, these are two figures from that Sal et al. 2008 paper, the seminal paper investigating lunar interior water. And we see the orange and the green symbols are color-coded for the different volcanic glass deposits. So orange are orange glasses and green are green glasses. And you see that they contain several tens of parts per million of water. What that group also noted was when they looked at these glass beads, they saw differences and correlations between measuring these volcanic glasses in the center, in the core, and also towards the rim. And they inferred that even though they were measuring lunar water, that there was evidence that some water may have been lost. So you see here the core of these glass beads contains more hydrogen, more water than the rims. They were able to infer some processes. Early on, Francis McCubbin and colleagues recognized that even though the majority of apatite in lunar samples is fluorine-rich, indicated by this chlorine-fluorine-OH ternary diagram, with most of the points falling towards this F equals 100 ternary apex, it was clear that there's some indication of OH in these crystals, and we've since been able to quantify that. Again, measuring in the parts per million to several thousands and more part per million water. And finally, coming back to the melt inclusions, if you look at the final figure, the Harvey et al. 2011 figure, here we're showing that, or here they were showing that those same melt inclusions I showed you on the previous slide contain hundreds to thousands of parts per million water. And actually they compared in their study the lunar volcanic olivine hosted melt inclusions, water content, to some terrestrial, albeit dry terrestrial, mid-ocean ridge basalt values. And they showed that actually they're very similar. And so that gave rise to the idea that maybe some parts of the moon are as wet or dry, however you want to look at it, as some parts of Earth's mantle. One important caveat to looking at lunar samples, and as we saw with the lunar surface, there are always caveats, is sample petrology and petrography is really important to be able to correctly identify and interpret what the water you're measuring is actually telling you. Is it telling you about magmatic processes, secondary processes occurring at the surface, or is it actually telling you about what was in the magma that generated that rock? Next slide, please. Thank you. And so the whole point really of looking at lunar samples and looking at the water that they contain is not just to identify that it's there, but to try and make some estimates about how much water is in the interior of the moon. And I just showed you some examples of water measured in lunar samples. We see a huge variation in the abundance of water in these samples, and that reflects, we think, the magmatic sources. So once you account for all those other processes that can change the abundances, you're left with a situation in which you still have some variation. And so if you calculate, or you can calculate the distribution of different volatiles, including water, between different reservoirs in the moon. So for example, between the crust and the mantle. And then you can start to play some games, understand how the water, the actual samples in the laboratory might be related to the thermal and magmatic evolution of the moon through time in a model like the lunar magma ocean model that we briefly introduced earlier. So once you know what the source regions, whether your sample is part of the crust or part of the mantle, then you can start to play some games and estimate the water content of the bulk silicate moon. And currently there's still a wide range of values from about 1 to 79 part per million water in the bulk silicate moon. But the important thing to remember is that, you know, in the Apollo era, we were talking about 1 part per billion water. We now have a significant revision of that estimate. Next slide, please. Now, right at the beginning, we talked about the isotopic composition and why that's important, and why looking at deuterium hydrogen ratio is important is because various processes like volatile loss or addition or mixing of different sources of volatiles can either mix or fractionate those isotopes, those deuterium and hydrogen isotopes. And so what we also want to do, in addition to understanding the abundance of water on the moon and inside the moon, is also to understand, well, where did it come from? And we can do that using isotopic fingerprinting, but in order to do that, which is kind of 2 steps further from where we are right now, we need to understand what the isotopic composition of water in the magma was first before we can get to that stage. And so right away, we know that volcanic rocks that have been measured for water from the moon have lost some volatiles. And we can see that with the naked eye. Here's a hand specimen over the orange glass beads, which is pockmarked full of void spaces. And that tells us that this volcanic rock at one point contained a lot of volatiles dissolved in the melt. And as that was extruded and started to cool, it lost those volatiles, including potentially water. And so the middle figure is showing you some work done at the Open University by Rova Tartez and colleagues, showing the water content on the x-axis measured in apatite versus the deuterium to hydrogen ratio, or this delta notation, this delta D value, on the y-axis. And all the symbols indicate, symbols with error bars indicate actual measurements. And so what they were able to do was reconcile those measurements with loss of hydrogen from the melt. And so they could actually explain that if you had a melt that's greater than 1 weight percent water, that tends to have a lower deuterium to hydrogen ratio, low delta D value, compared to apatites that they measured that have higher delta D values and lower water contents. And so by doing some Rayleigh degassing modeling, they were able to suggest that actually these samples are recording volatile loss and volcanic degassing, and that if you wanted to interpret what the original melt contained in terms of water and its isotopic composition, you would choose an apatite that has the highest water content and coincidentally has the lowest deuterium to hydrogen ratio. Other processes that we have to be aware of and try to account for when trying to understand the magmatic history and try to determine where the sources of interior volatiles came from are things like shock and space weathering, including solar wind implantation. And so some of Anna Cernok's work has shown in the final figure that shock doesn't seem to play an important role when looking at some of these crustal samples that we have from the moon. Next slide, please. Okay, so the bottom line with looking at the isotopic composition, at least from my point of view, the thing I find most exciting is that we can fingerprint the source of interior lunar water. Now, we can't do that for all samples because a lot of samples, especially the volcanic samples, have just had too much processing, either volatile loss through magmatic degassing, or they've undergone some interactions on the surface, maybe mixing with the regolith. And so there are really, as far as I can tell, only two groups of samples with which, groups of samples or targets that we can really understand the interior source of lunar water. Source of interior lunar water. And so we can use melt inclusions and their hydrogen isotopic compositions, and also the lunar highland samples, thanks to Anna's recent work, to give us a record of where the magmatic water inside the moon may have come from. And so this is because distinct hydrogen isotope compositions exist amongst different water reservoirs in our solar system. And so this is shown on the figure on this slide. So at the bottom, we have delta D value, or deuterium to hydrogen ratio. And so you can see if I had plotted 0, that would be where standard mean ocean water is. So that's kind of where, if you look to, VSMO's on there, so that's our standard, and everything else is a deviation from that standard. You can see that the sun is basically at -1,000 per mil. It's very depleted in deuterium. And if we go all the way up to the top, you see that comets show a huge range, but are generally very deuterium rich. And so because of these different water reservoirs existing in the solar system with different isotopic compositions, we can fingerprint where water in the moon may have come from. And so on the moon, we think, or inside the moon, we think that magmatic water and original water to the moon probably had an isotopic composition of between about 200 and -200 per mil. It overlaps with some of the estimates we have for the bulks of Earth and for volcanic rocks from Earth. But it also matches quite nicely with some of the carbonaceous chondrites that are shown in the middle of this figure. And so it's been hinted that there's probably a common heritage of water in the Earth-Moon system, potentially with some asteroids like 4 Vesta. Again, this is some work done at the Open University. Next slide, please. Okay, so if we think that water inside the moon has some link to or common heritage water in the Earth, then when and from where did that water get locked inside the moon? And there's really 2 end members that could be possible scenarios to explain this, but it could also be a mixture of these 2 things. So either water what survived the moon forming impact event and was accreted with lunar material after that impact, or volatiles, including water, were inherited later on. Not so late that the moon had already solidified and formed, but in the time period between this, the accretion of lunar material in Earth orbit and the solidification. So maybe a 200 million year time window after the moon formed. And so because we see this commonality between carbonaceous chondrite, water in carbonaceous chondrites, and also in lunar samples and potentially on Earth, potentially those are the types of impactors that may have been impacting the Earth-Moon system around that time. Next slide, please. And so a few years ago, we did some work basically doing a mass balance between adding water from carbonaceous chondrites, in this case CI carbonaceous Ivuna type chondrites, to and mixing them with different other different sources. So instead of just saying, well, maybe water was delivered late just from one carbonaceous chondrite, let's mix some carbonaceous chondrites with some comets, for example, labeled here as DEK, ORT, and DDK. And we find that the long and short of this is that water inside the moon and inside Earth is most compatible with water, the isotopic composition from water-rich carbonaceous chondrites, and it's not very compatible with water from comets, because comets are so much more deuterium-rich than what we see in any of the samples when we account for magmatic processing. Next slide, please. Okay. So going back finally to our models for lunar water, we mentioned that after the Apollo era, moon formation and also lunar magma ocean evolution didn't really take into account that there might be water present. And so one of the big questions that came out of the detection of water in lunar samples and at the surface is, well, what do we do now? How can we refine our models to include water, and can that indicate to us when water may have been included into the moon? And so some of the new models are suggesting that actually hydrogen-bearing species can be retained even through such an energetic event such as giant moon-forming impact. And in addition, experiments and some theoretical modeling have also suggested that water is compatible with the lunar magma ocean. So you can create a crust, experimentally, you can create a crust on the moon with a similar thickness to what's observed on the moon today. You can account for that by having water inside the moon during the magma ocean stage. Next slide, please. But there are a lot of unknowns, and I kind of hinted to some of the unknowns with regard to surface water earlier on. But more generally, water on the moon, there are a lot of gaps in our current understanding. So we think we know to some degree the origin of lunar water, but it's possible that there are multiple sources. It's possible that we could have had survival of material during the moon forming impact, or it was delivered later. But we don't really understand, or we're fairly restricted at the moment because we haven't sampled a wide geographical area on the moon. And so we need to go and look at more samples to basically test those hypotheses and see if they're right. We also need to understand how heterogeneous is lunar water inside the moon when we compare samples taken from the far side compared to what we have from the near side. We're only starting to understand how space weathering affects the record of magmatic water hosted in lunar minerals, glasses. And there seems to be there's somewhat of a disconnect between interior and surface water. Something I forgot to mention earlier is that another source of lunar surface water is potentially outgassing or degassing of these volcanic deposits as they're erupted onto the surface. And then, of course, what is the character distribution and abundance of surface water? And so this leads me on, next slide, please, to kind of look into the future. And hopefully I'll try to wrap this up relatively quickly. Please. Okay. So one of the things I wanted to talk about really quickly is, before we get on to looking at the future of lunar exploration at the surface, is to talk about what we're doing to look at a new group of samples and how that's going to help us help inform our understanding of lunar water going forward. And so this is NASA's Apollo Next Generation Sample Analysis Program, which was released in order to try and maximize the science derived from samples returned by the Apollo program in preparation for future missions in the 2020s and beyond. And so NASA had the foresight to set aside some samples in the 1960s and 70s, essentially withhold them from study by the community, and they stored them under various special curation techniques. And so some are unopened core samples, some are vacuum sealed, some samples they stored frozen, and some samples they stored in helium. So NASA solicited proposals specifically designed to look at these unopened samples using new technologies. And so the idea behind the program was that you had to propose something that couldn't be done on the current sample collection, but could only be achieved on these specially curated samples. And so NASA selected 9 teams to do a variety of different investigations. Next slide, please. And I'm going to talk about those today. So one is volatiles, or water in Apollo 17 basalts, and that's a group that I'm leading here at the University of Arizona. And then the other is the wider ANGSA core consortium and preliminary examination team. So next slide, please. This is going to be short because we have not made much progress, but I do want to give you a little bit of an introduction. So our group is looking at, or chose to look at, a group of 4 basalts, volcanic rocks collected on the surface of the moon at Apollo 17 from Steno crater. If you want to click forward a couple, there we go. And so three of the samples are currently stored in ambient conditions, so room temperature, under continuous flow of nitrogen. They've not been very well studied, and they include these three samples that you see here: 71035, 71037, 71055. And they've been available for study since they were brought back, but they just haven't been studied that well. And then there's this special sample 71036, which has been stored frozen at -20 degrees C for almost 50 years. And so we wanted to compare and contrast these four samples. Yep, you're okay, next slide. And you can flick through all of these as well. Thanks. So we wanted to do a very comprehensive laboratory investigation of these four samples. And to compare the ambient samples with the frozen sample. Our analytical campaign involves assessing 3D mineralogy and morphology, 2D mineralogy and petrology, doing volatile analysis, including assessing the water content and hydrogen isotopic composition of the samples, and also to determine an eruption and surface age of the samples. And the main questions that we want to address are, with regard and relevant to this talk, are what is the water content and signature, what does the water content and its signature isotopically look like between the ambient samples and the frozen basalts? And can we say anything about curation practices, i.e. do we need to start curating samples in frozen conditions? We want to understand, do these samples record a history of volatile degassing? Can we see similar patterns in the water content and hydrogen isotopic composition as was shown in some of those previous studies, and can we actually see that occurring in the samples? Can we tease out a magmatic signature of water, and can we determine the origin of lunar water, this collection of Apollo 17 basalts? And also we want to understand how old the basalts are. And yes, they were chipped from the same boulder, but does that mean they're from the same lava flow? Can we say something about volcanic activity at the Apollo 17 site? And if you go to the next slide, we've been hampered a little bit by COVID-19, but some of the work that a PhD student in my group has been working on is looking at the 3D modal mineralogy of the samples. And what you're seeing on the screen is a composite video of the 3D morphology of one of these samples. So it's a micro-computed X-ray tomography scan of the sample. And what you're seeing in blue is basically the mask of the exterior, and then in yellow are ilmenite crystals, so iron, titanium-rich minerals that occur all throughout the sample. And so what Zoe's been doing is comparing the 2D mineralogy that we see in rock thin sections with taking slices of these taking the bulk of these 3D videos and assessing and comparing what we see in 2D to what we see in 3D. And if you look at the bar graph on the side here, we do start to see some differences between the modal proportions of heavier silicates, things like olivine and pyroxene, lighter silicates being plagioclase, and then the ilmenites and the really high phases. Please. Okay, so we haven't made a lot of progress, but now things are starting to open up a little bit more. We'll be able to get cracking with understanding the water content of those samples. So I just wanted to introduce you real quickly to the core consortium. You can go to the next slide. This is a team of over 50 researchers from around the world. It's led by Chip Shear from the University of New Mexico. And it includes Professor Anand and other colleagues at the Open University and University of Manchester. And this core consortium is formed of members from almost all of the 9 teams that were selected. And the important thing is this is a double drive tube that was collected at Apollo 17 in the Taurus-Littrow Valley. And being a double drive tube, there are 2 parts to this core sample. You can see here video stills from one of the astronauts actually collecting this on the lunar surface. Go to the next slide. We'll just skip that one. So why this is important is because this double drive tube, we think, we know, was collected at Station 3. You can see that on the top image collected at station 3 on top of this light mantle deposit that you can see there. It also occurs very close to the Lee Lincoln Scarp. And we think that this core sample is actually sampling a landslide deposit. And so could give us insight, because it's a stratigraphy that we're going to see with the core, could give us insights into material from higher up in the South Massif, as well as from the floor of the Taurus Littrow Valley. Next slide, please. Okay, so the core is divided basically into two parts. So there's the uppermost part, which is numbered 73002. It's about, we think, between 0 and 22 centimeters. That's how much it's sampled below the surface. And that core was not sealed on the moon. It was, and it was opened last year, and I'll talk about that in a second. The bottom half of the tube, though, of the core, so from 22 centimeters down, has not been opened, and it was sealed on the moon, vacuum sealed on the moon. And that's important because we think that that bottom part may have contained volatiles. It's deep enough in the regolith that maybe contained some of these surface volatiles that we were talking about earlier on. And we think the temperature of collection was cold enough that maybe some of those ices might have been present during collection. They wouldn't be present now, but because it's vacuum sealed, there may be isotopic and chemical signatures of whatever those ices were still trapped within that core sample. Okay, next slide, please. So in addition to understanding surface processes and volatiles and just understanding the geologic diversity of the site, the core is really important for understanding those things, and also understanding geochronology of the site and volcanic activity, etc. Now, the first core, the top part, 73002, was opened for the first time last year. What you're seeing on the screen is a microcomputed X-ray tomography scan of the core. It's showing you the vertical distribution of class and different minerals within the core. Brighter materials have a higher atomic number than, or higher density, if you like, than things that appear darker, blacker, or more black. What you're seeing on the right-hand side of the screen, you see two tubes laid out horizontally. The bottom image is showing you what this was scanned in the 70s using the technologies available. And you see that the X-ray scan from most recently from last year is much more detailed. We see a lot more variation. We see can start to pull out different class and materials within that core. Next slide, please. And the neat thing about using this newfangled technology to basically X-ray scan lunar samples is that we not only get a 3D video, but we can take slices through that to understand. Here you see one portion of the core to understand the lithologies that are present. You can see it's a very complex mixture of lots of different things, including a basaltic class. We can see lots of breccias and a very fragmented appearance. And so the procedure, once you have samples like this is basically being run as a new sample return mission, if you like. We've opened a new sample. The curation staff then need to go through and dissect this core. And so having the microcomputed X-ray tomography data really helped the preliminary examination team, the people actually going through, doing the dissecting, noting down what class are present, give them a great idea of what was to come. Next slide, please. And so in December, I was fortunate enough to go to JSC and be part of the preliminary examination team along with student Zoe Wilbur. And this photograph showing you Charisse is one of the curation processors. She's actually doing the dissection, actually picking up this core that you see laid out in the glove box. And picking out, you can see some pretty big clasts on the little foil tray in the just below the center of the image. Picking out those clasts, which would then be themselves imaged by computed tomography before we start physically breaking those apart and sending them out to the team. Okay, so let's move on. Next slide, please. So we can learn a lot from samples that we have in the collection. We've been learning a lot, as we've talked about, but we still have a lot of scientific strategic knowledge gaps that we need to fill. That, yes, we're going to try to address some of them through this program, but we really need future lunar sample return in order to fill a lot of the knowledge gaps we have about the moon. And so here's a list of just some of the materials, some of the wish list materials of things that I would like to see returned that would really help us to better understand our nearest neighbor. Next slide, please. Oh, some of on this list is young Maori basalts. Next slide, please. Yeah, you can go to Chang'e. And I couldn't not talk about the Chang'e 5 mission. So right now we are in probably the golden era of sample return missions, not just to the moon, but also to other extraterrestrial bodies. And so Chang'e 5 is a mission that landed about a week ago now on the surface of the moon on the near side. And its mission was to collect about 2 kilograms of material from the lunar surface. It lifted off the surface last week, and it's expected to deliver new lunar samples to Earth next week. Please. And so one of the most interesting things about the Chang'e 5 mission is it's been long known that we have a problem in our extrapolation of crater counting from the moon to planetary bodies, because we're limited by lunar samples, which tend to be quite old. So most of our volcanic rocks from the moon, the youngest 3 billion years old, but we know from remote sensing that volcanic activity on the lunar surface occurred well into the last billion years. And so Chang'e 5 landing site actually targeted some of these really young lava flows on the lunar near side. And so the globe is showing you in green the Apollo missions, in red, if you can squint to make them out, are the Luna missions. These all collected samples on the near side. The black circle is showing you where Chang'e 5 landed. And so if we move across to the left-hand side, this panel is showing you the projected landing site where they wanted to land. And the little blue box is showing you a feature that is present in this bottom panel, which is showing you the red stars where they actually landed. And so you can see that the Chang'e 5 mission was hugely successful in landing within their predefined landing ellipse. So it'll be really exciting to see what ages and geochronology and geochemistry and water contents the scientists involved in that mission are going to be able to tell us about those near side young lunar basalts. Do we fix the crater counting curve with those samples? Because the young basalts are, we think, between 1 and 1.5 billion years old, so significantly younger than anything else we have, frankly, from the Apollo missions or Luna missions. Next, please. I'm almost there, I promise. And so, could not show you this slide. So this is a landing site panorama from that Chang'e 5 mission, showing you the beautiful lunar surface, very flat area that they landed in, and you can see potentially some volcanic rocks just there on the surface in front of the next slide, please. So going forward, NASA has a long vision program to send humans back to the surface, potentially in 2024. But before that happens, there's a whole fleet of missions that are going to go back to the lunar surface starting next year, starting with robotic landers and also investigations targeting in situ resource utilization, and to ground truth what's going on in the polar regions, and to really try to understand, at least initially before we send humans, are there resources at the lunar poles that can be used to support and sustain not only lunar exploration activities and humans living and working on the moon, but also to sustain future exploration to other places in the solar system. Next slide, please. And so I just wanted to say as well that it's not just NASA's program that is hoping to go back to the lunar surface with robotic missions and eventually humans. Part of that is NASA's Viper You can see here this rover, but also ESA and Cosmos are planning to go back to the lunar surface potentially in 2025, to do in situ studies of volatiles, including water ice on the surface of the moon, all at the lunar polar region. Next slide. I think this is my second to last slide coming up. Okay, and so yeah, future lunar exploration with Artemis will end with Artemis. Will culminate with Artemis 3 in 2024 potentially, with humans being on the surface. Next slide and last slide. Okay, so I just wanted to finish off by saying the water's been detected in lunar samples and at the surface, but there's a huge discrepancy between what we're seeing, not just in terms of interior water and surface water and how do we connect the two, but also with regard to surface water, the amount, character, and distribution and the sources, and also the cycling of water on the surface, and how sustainable are these deposits that we see. But all of that kind of uncertainty is actually giving us the motivation to actually go back and constrain both of these things in more detail in order to help us better understand not just the resources that are there that might enable future space exploration, but also just to better understand how our moon formed, evolved, and how it continues to evolve today. So thank you very much. I'll leave it there and take any questions that come through. I have no idea how long that was because I had that little blip at the beginning.
Did you hear the round of applause?
No.
I tried to throw that in. It wasn't picked up by my mic. You hear that?
No. I can hear some rustling. It's good enough.
Okay, maybe my headset's doesn't pick up that very well. So thank you so much, Jess, for that talk. That was really, it's super interesting, and I learned a lot. Given that this research was going on under my nose, I think that really kind of highlights how much world-leading stuff is going on at the OU in collaboration with other international world leaders in these sorts of areas. So that was really good. I think everything went well. After the connection issue at the start, everything seemed fine. I think we can blame the American residential internet network for that one. So I know you need to get away by 9, so that's due to other commitments. So that's in a few minutes. So
okay.
Maybe if we,
okay.
So we'll ask a few questions that have come up already, and you said you're happy for us to forward any other questions that come up, and we'll feed those back to the people who asked them. So don't worry if your question doesn't get asked live on the stream. So first question is from Mark, and he asks if academics like Professor Paul Hain of the University of Colorado are saying that this water will provide NASA water for drinking and rocket fuel, is this a renewable resource, or does the rate of replenishment by solar winds and micrometeorites, or whatever means, that this is going to be like fossil fuels on Earth and eventually run out if we let it evaporate or if we use it as reaction mass? Should we be flagging up the use of this water resource as an ethical issue from the very start?
Okay, so thank you very much for the question. So I think we are considering that polar ice deposits are more akin to fossil fuels because of we think that, the lunar surface has, except for the space environment which it's been exposed to, volatiles have been continually raining onto the surface for over 4 billion years. And so on a geological timescale, maybe they can be replenished, but no, I think it's more fossil fuel-like. And so there are concerns that, we might end up using all of those resources for, future exploration. There's also, I kind of try into this. So NASA have plans to go back to the moon and characterize volatiles and utilize volatiles, but a number of other space agencies and international partners are planning to do the same thing, and not to mention commercial enterprises. And so there is this interesting atmosphere emerging where we're going to have to start to consider, and everyone wants to go to the lunar South Pole because it's the place where we see the most stable PSRs, where we see a lot of enhancement in hydrogen and water ice on the surface. And so they're very popular areas. If you see any of the exploration plans from various agencies, the lunar South Pole is the place to go. And so there are these rising tensions about how to not only utilize it in a way that kind of maximizes the effectiveness of those in enabling future exploration, but also in sharing. And so there's interesting activities going on to see how that actually happens. But I don't know of any agencies that are kind of that at the agency level working bilaterally to do that. I think there are a bunch of people in the community doing that, leading community efforts, and kind of trying to make the agencies realize that it's something we need to consider, because they're not going to be sustainable, and they're finite, at least on our lifetimes and timescales.
Okay, great. We've got another question from Diana here. She asked if a common origin of Earth and Moon water suggests that a lot of Earth water may have been delivered before heavy bombardment. What do you think of this implication?
Okay, that's a great question. And so something that often, or something that I did not clarify in the talk, there's this idea that around 3.9 billion years ago, there was this kind of late surge in bombardment of the moon, and that's what created a lot of the basins and large craters we see on the surface. The late heavy bombardment that idea is kind of going away now, but if we consider that scenario, that occurred about 3.9 billion years ago. The kind of water accretion that I'm talking about, kind of going in, adding water to the interior of the moon, occurred much, much earlier. So between the formation of the moon at about 4.4 billion years ago to the time when the lunar magma ocean essentially shut off at probably about 4.2 billion years ago. And so these are two very different time frames, but it's interesting to think about because, as I said, surface volatiles are recording the impact history of the entire moon's history. So any asteroids, wet asteroids, or cometary material that impacted the surface between its formation and the present day will in some manner be recorded in the lunar regolith and potentially sequestered in the poles. And we might see signatures of those bodies, and maybe there was a change in the flux of different types of materials over time, which might be recorded in those deposits.
Great, thanks. Diana also has another question. Could there be accidental volatile enrichment due to freezing the samples?
I don't think so, because when the lunar samples are brought back, and I didn't say this, but the sample, at least that we're going to get, it was brought back to the lunar receiving lab, and then within about 2 to 3 weeks, the records are a little hard to read, but we think within 2 to 3 weeks, that sample was frozen. So you saw a photograph of that sample. So clearly, at least some photography of the sample had taken place before it was frozen. But the whole time that it was kind of outside of the cases in which the Apollo astronauts brought them back, they were put into glove boxes. And so those glove boxes have very minimal, they're almost pure nitrogen, they have very little water in them. And so I think it's unlikely that there would be any addition of, volatiles or water ice into the samples just from freezing at those temperatures. So I think it's likely, but it's something we'll be looking out for. Any differences we see between the ambient samples and the frozen sample is probably going to tell us something unique about curation processes, and potentially we can make some inferences and maybe some recommendations based on what we find.
Mm-hmm. Great. I'm not sure if you touched on this in your talk, but we've got a question from Stacey that asks if you're able to see if the isotopic composition of the water changes with some kind of timescale, according to the age of the samples that you're analyzing.
So that's a very interesting question. I didn't mention it in my talk, but It seems like some of the very ancient samples that we have from the lunar crust and some of the lunar highland samples, some of Anna's work that I mentioned, and also some of the work I did during my PhD, those samples seem to have a almost remarkably consistent isotopic composition. But then when we go to, and they're relatively old, somewhere in the range of 3.9 to 4.3 billion years old, those ancient samples. But then if we go to the lunar volcanic materials, which span a range of between about 3 and 4 billion years old, they show a huge range in their isotopic compositions. And in some cases, it looks like between different chemical types of volcanic rocks, there are some differences. And so it's not as clear to me that, you know, with time, you've had a change in the isotopic composition, but more there is this correlation between different magmatic or different rock types. So different rock types have slightly different isotopic compositions and water contents, but we think that that's telling us more about the thermal and magmatic history of the moon as opposed to maybe a change in impactor flux or something like that over time.
Okay, great. I think this is quite an interesting one from Dave. He says that planned near future large hydrogen or oxygen fueled lunar descent and ascent rocket engines will rapidly inject approximately tons of water exhaust products into the lunar water cycle. He's just asking if you have any comment on how that will affect the science.
That's true. That's true. And actually, there's been some work recently by some colleagues, I think, at Washington University, St. Louis and PSI, looking at Apollo era kind of implantation of exhaust. So it is a concern for someone who's interested in exploration, but I guess more interested in science, if I can say that. You know, it makes it that much more important to go and do a lot of prospecting missions before kind of then ascending from the lunar surface using resources that we've kind of mined at the lunar surface. And so that's exactly what the plan is from multiple different space agencies, is to go start looking at and better characterizing those deposits starting next year, and then send some robotic missions to go and look at in situ what those materials look like, go and send a rover, see how it varies, you know, in the transect of the area that a rover can traverse. And then eventually, you know, this is a very iterative process. You build up your technology and your knowledge over time. And so it will be, you know, it'll be some time before we're actually at that point where we're at the point where we have hydrogen and oxygen extracted and mined to be in that position. So hopefully we've done a lot of the science before then, that it's not actually a problem. But of course, you know, you're in the vacuum of space. Anything you kind of put up is either going to go and be lost to space, or it will rain back down and condense on the surface of the moon. So then you're going to have an anthropogenic kind of source of lunar surface water as well.
I assume when they're planning these missions, they try and take that into account, do they?
I don't think we're at that point yet. It will be taken into account, you know, when we start looking towards Mars, and how does lifting off the surface, you know, impact lunar science and lunar exploration. But I guess I'm not as involved in those discussions right now.
Okay, there's an interesting question from Peter here. He says that on Earth, the seas contain less water than the total that there is in rocks. Is there an estimate for the moon of how much free water there is and how much bound water there is and how that compares?
So as I mentioned at the beginning, you know, free water on the moon means something very different to what it means on Earth. So Earth, as this person has said, you know, we have surface water in oceans and lakes and also ice. But on the surface of the moon, we're more talking about kind of monolayers of water that are attached or kind of like stuck to grain surfaces. We're talking about water bound into minerals, and then we're talking about potentially buried ice. in these patchy horizons in PSRs and elsewhere on the surface. And so in terms of what this person is asking, I kind of touched on what we think is bound up within the moon. But with regard to the surface, there's so many unknowns with respect to the different data sets we have from orbit that, there's such a wide range of the potential water estimates. I've seen estimates ranging from, tens of millions of tons of water ice potentially at the surface to even more than that. And so it's such a huge range in the surface. But I guess the take-home message is that the moon is dry. It's not as dry as we thought it was, but it's still drier than Earth.
Okay, fantastic, interesting. So I think I'll just ask one last question.
Okay.
Yeah, this one's good. So if you could decide where a lunar mission would land and get samples from, where would you send it?
I got asked this question last week, and my gut reaction is go and land on the youngest volcanic deposits. And so I'm really happy that, the Chinese Space Agency have gone, they've done that, and hopefully we get back those materials. But the next place I would go would be the Lunar South Pole. For me, I would want to go somewhere where there's the opportunity not only to go and better characterize some of these polar volatiles, but also to understand better the local geology. So the Lunar South Pole, I didn't mention this, is really interesting, not just for volatiles, but because there's also the largest impact basin on the moon in the south, near the South Pole. And it's a huge basin, and we think it formed very, very early on in the moon's history. And so being able to date impact melt from that event would also help us to better constrain that crater content, potentially pin it further back in time than we currently can. Also, there are lots of things, there's boundless rock types at the Lunar South Pole that we just don't have access to in the Apollo collection, even from lunar meteorites or in the Luna collection. So going to the South Pole and doing sample return from kind of anywhere there would be really interesting from my perspective.
Okay, fantastic. Well, I think we'll leave it there for now. I'm sorry to those members of the audience who have sent in questions that we weren't able to get to today, but Jess does need to dash off to another meeting. So thank you so much again for your time today, Jess. I think it was a really interesting talk, and it was a bit different from the normal types of talks that we have here. I'm a bit more chemistry and geology than I'm used to, but I really enjoyed it, and I learned lots of new stuff. So thank you so much. I would just ask anyone who's still with us, please, if you haven't filled out the demographic survey, the link's there on the page. Can you please just spend a couple of minutes of your time doing that for us? That really helps us to get out to a wider audience with these sessions. Other than that, I think I'll say goodnight to everyone. I think it was a really good talk. The next planned one that we have is February the 9th. Professor Nick Braithwaite will be talking about something, details to be circulated close to the time. And hopefully, if you keep an eye on the mailing list, we'll have something in place for January the 12th in the new year. But I'd like to take this opportunity to thank everyone for coming to this new session of lectures as they went online, and hope you stick with us, and I hope you all have a Merry Christmas and Happy New Year. So thank you so much.
Thank you with the technical difficulties.
It had to happen at some point. I'm glad we had me and Alice here to field it.
Thank you. Thanks everyone. Thanks Ben. Thanks Alice.
Cheers. Bye.
Bye everyone.